Hello, students! Here we're going to be looking at derivatives of logs and exponentials. I've had you kind of play with some of this stuff already by looking up the rules. Today we're going to show where those rules come from now that we know some implicit differentiation stuff. All right, the first thing that we need to think about is dealing with inverse functions. And I want you to pause here for a second and just kind of brainstorm what you remember about inverse functions. All right, if you're thinking about switching x and y, that would be a great place to begin. If we're thinking of some examples, we think of things like the natural log of x, and e to the x is definitely everybody's first example. Things like x squared and square root x with some limitations, x cubed and the cube root of x, and things like that. One of the ones that we're going to use a lot today is dealing with the natural log of things going forwards and backwards. All right, I'm going to move this so I can read it a little bit. I've added this weird function to a graph in Desmos. Like we did with some trig stuff, we're going to have to think about this graphically in order to make some sense of this. What we want to think about is the limit as, I want to say x approaches 0 here, of e to the x minus 1 over x. And hopefully we can see that this limit is going to have a value of 1, even though that point doesn't exist. All right, so the derivative of e to the x. All right, definition of derivative. It's been a bit since we've used this for this type of thing. Of e to the x plus h minus e to the x, f of x plus h minus x, f of x rather, over x plus h minus x, which is just h. Cool. I'm going to go one step further, and I'm going to rewrite this as the limit as h approaches 0 of e to the x times e to the h minus e to the x using exponent rules, and that's going to be over h. I'm going to factor out an e to the x. That's the limit as h approaches 0, e to the x times e to the h minus 1 over h. And I'd like you to notice that now we have something that looks like this, except with h's instead of x's. So what we end up looking at is that this limit for this part is going to be 1. And if I plug h equals 0 into e to the x, I'm left with just e to the x, which is a weird thing. This tells us that the derivative of e to the x is going to be e to the x, which is strange. There are some reasons why that happens, and it's based on growth rates being equal to population proportions, but that's okay. The other thing that we're going to begin seeing is some weird notation that I like, where I'm looking at this as the derivative of e to the stuff, because now we know the chain rule. So we can say that we're doing the derivative of e to the stuff is going to be e to the stuff, but then we have to always remember to include the chain rule, so we'd have times the derivative of that stuff. As an example, if I've got e to the 3x squared, the derivative of this would be e to the 3x squared, then times the derivative of that stuff, so times 6x. So we have to use the chain rule. We got to be a little bit careful with that today. The other kind of spoiler here that we're going to see on the next page is based on this idea. What function can we now find the derivative of given what we've discussed thus far today? Well, we talked about inverses. We talked about e to the x, and I'm guessing that means that we can find the derivative of ln of x. Oh, and look at that. All right, the derivative of ln of x. Well, let's start with this. So if y is equal to ln of x, our goal is going to be to find what dy dx is. We don't have a way to do this directly yet, because we don't know how to deal with derivatives of natural log. So instead, I'm going to convert this to e to the y is equal to x. That's converting between log and exponential form. This is really kind of about the inverse of these things. Now I'm going to take the derivative of both sides. And the derivative of e to the stuff is going to be e to the stuff multiplied by the derivative of that stuff. Ooh, the derivative, I'm just going to write that out for a second. So derivative of y, and then derivative of x is going to be just 1. Okay. Well, there's our y prime. That's what I'd love to get by itself. And in doing that, I'm going to end up with, so we've got y prime, or dy dx. I wrote that dy dx up there, so I'll do the same thing here. Is equal to 1 over e to the y power. The last thing I'd like us to think about here is that this is in terms of y. We'd rather have this in terms of x. But we have a way to think about e to the y in terms of x. E to the y is equal to x. So this is actually 1 over x. The kind of weird result of this is that the derivative of the natural log of x is 1 over x. That also means that the derivative of the natural log of stuff is going to be equal to 1 over stuff multiplied by the derivative of whatever that stuff is. Dealing with logs in general, we can do the same type of thinking. So let's say that we're looking at, I don't know, log base a of x. Well, we know how to do the derivative of a natural log. Would it make sense to try to convert this into a natural log? I've seen quite a few of you use change of bases on spirals, so I'm okay with kind of talking about that. I could write log base a of x as ln of x divided by ln of a. And if that's still equal to y, that's fine. Ln of a is just a constant. So if we're thinking about this as like 1 over ln of a, that's a terrible ln, there we go, it's a little better, times ln of x, then the derivative could be written as 1 over ln of a times 1 over x. So we end up with 1 over ln of a times x on the bottom. This is not all that useful of a thing for us to do and spend lots and lots and lots of time on. One of the things that we can deal with this is to find derivatives pretty quickly of any log function. For the most part, we're going to stay in the realm of ln because it's a much more useful base for us to work in. For general exponential functions, so we're looking at like a to the x, we could do the same type of thing where I might convert this to log form first. So we're looking at this as log base a of y is equal to x. I could then take the derivative of this, and I'm going to end up getting, based on the rule we just did, 1 over ln of a y, and that's the wrong variable, so that's times y prime, is equal to 1. I'm going to multiply that to the other side so I can get that by itself, and we get y prime is equal to ln of a times y, which is a to the x. So the derivative of that is going to be ln of that base multiplied by that same function, a to the x. Again, this one's marginally more useful than logs of other bases, but you've got reference sheets you can use. We tend to stay in base E, so we can use natural logs. Probably not going to be using this. And here are all of our derivative rules so far. There's some practice, and these are all the ones that we've looked at today.